Welcome to the first demonstration video for the reverse engineering course of Proffesional Security. This is the first of a series of videos through which we are going to examine together the technical challenges of this course. So sit down, relax, and let's learn together by having fun. This video is associated with the chapter number 5 of the reverse engineering course. As already mentioned during the introduction of the 5th chapter, the most important and necessary first step in reverse engineering is to manage to locate the algorithm or the algorithms that we are looking for. This is of course not always a trivial task. However, depending on the case, it is something that we can achieve through different ways. In this chapter, we discussed about the most simple way to achieve that. And this is of course through string references. And as already said, by string reference we mean an assembly instruction that refers to a memory location where a string is stored. We will now start by doing some behavioral analysis of the application. So let's run the target executable and observe its functionalities. So let's enter a random code here. Press on check button, and we see that the application responds with a message box that says that the code is invalid. Of course, we didn't expect anything better than that, but we shouldn't be disappointed, because now we have a clue to search for inside the code of this application. So in this case, we possibly have two different ways of main execution paths. So the application, it will either accept the code or it will not. Of course, at this point, we still don't know what would be the output in case we put the right code. However, we know the result of the wrong input. So we can use this in order to trace back the execution and find the algorithm where the decision was made. So let's load the application with Oli Debugger in order to dig deeper. At this point, we are at the entry point of the application, which in this case, it's a short unconditional jump that brings the execution here. This entry point is generated by the compiler, it's not written by us. And you can also observe the first API that's going to be called, which is the get module handle A with parameter push 0. It means that it's going to return the base address of the module that is calling the API. So if I put a breakpoint just after this and run the application with F9, we're going to see in EAX the address of the image base of the executable module. So let's go back with the analysis and search for the clue we found before. So we do right click, search for all reference text strings. Now in this case, we don't really have to search for the string reference we are interested into, since we can see it among the top ones. However, if you would have to do that, then you can just right click, search for text, enter a substring of the string you're looking for. You can check the entire scope and uncheck the case sensitive. So press OK and we match the first one. Then you can press Ctrl+L to search for the next one. And we can see there are no other string references regarding this string. So let's double click on the string reference we were looking for. And this is going to bring us inside the code where the actual instruction is located. Let's see what we have here. We can see the message box called twice. In this case, is going to show the message we saw before. But here, if the message box is going to be called, it's going to display the message that says that the code was valid. So now we have to find where this decision is taken. As we can see here, there is a conditional jump that if it gets executed, is going to bring the execution here, which in this case the parameters for the message box we saw before are going to be pushed and the message box API is going to be called. But if this conditional jump is not going to be executed, then the execution will continue from here. So we're going to see the message box that says that the code was valid. Then this unconditional jump is going to be executed, that is going to overpass those instructions and bring the execution here, which means that this message box regarding the invalid code will never be displayed. Now let's scroll up till the beginning of this function in order to see if there are any other conditional jumps that could bring the execution here. We see this one is going to, if it's executed, it's going to redirect the execution here, then this one, and we see that only this one, if it is executed, is going to bring us here. So let's examine a little bit more the instructions executed before this jump. We can see that here there is a call to a specific function that is located in this address here, and then we see a test EX instruction which actually checks if EX at that point is 0 or not. If it's not, then this conditional jump is going to be effective and it's going to bring the execution here, which means that we are going to see the message box regarding the invalid code. But if EX at that point is 0, we are going to see the message box regarding the valid code. But let's see this in practice. We are going to set a breakpoint here by pressing F2. Then if you press on C button here, we are going to go back to the instruction that is going to be executed. Remember, we stopped here, so we're going to remove the breakpoint from here by pressing F2, and we're going to press F9 to run the application. So let's try again to put a code. Press on check button, and as you can see now, we stopped here. In this chapter, we're not going to analyze that function in detail. However, it is good to observe some key points. For example, if you observe the stack, you can see two strings pushed as parameters just at the moment when this call is going to be executed. We can see the code we entered and another one. So probably this function here in this address is going to evaluate if the code we put matches the one above. However, in this chapter we are not doing algorithm analysis in detail. We just try to understand the logic of the execution based on some simple observations. So now that we have a generic overview of the logic of this application, we are going to hack it in such a way that the application will always choose the execution path of our choice. And of course, in this case, this is going to be achieved by patching the conditional jump at the address 42E76. For now, let's continue the execution of this application. So let's press F8 once in order to execute the code in this call and stop at the next instruction. So we see that at this point EX equals 10. So we press F8 once more and then again to step over once more, and we see that in this case this jump is going to be effective because when this instruction was performed, EX was not 0. And you also can now see that the 0 flag is not set. So this conditional jump is going to be executed. Let's press F8 once and let's keep pressing F8 till we execute the message box call. So you see, now we have the invalid message. Let's press OK and we stop at the next instruction. So let's restart the application. Let's run it, put again a code of our choice, press on check button, and stop again at the same point. Let's continue stepping over the instructions till we get to the conditional jump. So we're going to analyze now this conditional jump. As you can see, this instruction is a 2 bytes instruction. The first byte is the opcode, the operation code of this instruction. The second byte indicates how many bytes this jump is going to skip if it is effective, as for example in this case right now. When you see this line marked as red, it means that the jump is effective and is going to be executed and redirect the instruction pointer here, which is the destination address of this conditional jump, as also the debugger disassembles and decodes this instruction. Generally, when we want to patch a conditional jump, we have 3 different options. We can either knob the entire instruction by right-clicking, selecting binary, then fill with knobs, which means that we're going to substitute both of the bytes of this instruction with 2 no operation instructions. So we're going to have the desired result. When the execution comes here, it's going to continue and display the message box of the valid code. Since the next instruction that's going to be executed is this no operation instruction here, let's start pressing F8 to start stepping over in order to see this happening. So now the application displays the message box that says that the code is valid. So let's now try and do something else. Let's run the application with F9, press on the check button again. So let's restore back the original instruction by selecting again undo selection, and this time we're going to modify this conditional jump in another way. We're going to use binary edit and only zero out the byte that indicates the number of bytes that this jump is going to skip if it's going to be effective. So let's press F8 once again. Now we have arrived over this jump instruction, which is the next instruction that's going to be executed, and as you can see, the red arrow says that this jump is effective, but now we have modified the number of bytes that it's going to jump with 0, which means that it's going to continue directly with the next instruction, which is actually the same effect. Let's keep pressing F8, and again we can see the message box that says that our code is valid. Let's now try something else on this jump. Let's continue the execution again with F9. Again, press on check button, and once we arrive on this instruction, I'm going to restore it back, and this time what I'm going to do is that I'm going to modify the instruction with the inverse of it. For example, I'm going to put jump if 0. So what I'm actually doing in this case is that I'm inversing the logic, which means that now for every invalid code, the application is going to display the message box that says that the code is valid. But if you actually give the correct code, the application is going to say that the code is invalid. So by using this jump, by modifying actually this jump with the inverse of it, we actually inverse the logic of the check. So again, now in this case the code that we have is not valid, but since we inverse the logic, the application is going to accept it. So let's just press F9, and you see that it says that our code is valid. So let's now try something else. Let's press again on the check button, and when we break again on this call instruction, let's observe the stack. So we can see the code we entered and another one. So probably that one, above our code is the right one. So let's again search for all reference text strings, and here it is. Right click, and we do copy to clipboard the text string. So let's run the application, and this time we're going to copy paste the other code. Press on the check button. So now you see that the two codes match. However, since we have inversed the logic, now the application, when it receives the correct code, is going to say that this code is not correct. Indeed. And just for the sake of verification, let's restore this instruction back and use the correct code without any code modification. Check. And the application correctly accepts the code. So we also know that actually that code was the correct one. So till this point we managed to do some memory patching and observe what were the results of those modifications. However, as already said, these are modifications done in memory, which means that they are only valid for as long as this process is actually running. When we shut down this process, when we terminate the process, these changes are going to be lost. So we need to permanently patch the file itself, the executable file itself, in order to make these changes permanent. So what we can do is go back here in the jump instruction, and let's fill it with knobs as we did the first time, and then right click, copy to executable all modifications, then select copy all, then save file and save it with another name, let's say patched, and let's shut down this one and let's go and run the patched one. Let's put the random code again and press on the check button, and we see that it accepts our code. Now what you can do is you can try by yourself patching it using also the other ways we demonstrated, and evaluate the results by yourself and play with it for as long as you want. However, there is one more step that we should go through together during this video, and this is of course the manual calculation of the offset of the byte that we want to change inside the file itself by just knowing its virtual address in memory. So let's run the application again. Put a random code or whatever. So we stop here again. Let's press F8 to stop here. So we know that the virtual address of this instruction is 42E76, which is actually the virtual address of the first byte of this instruction. The second byte is located at this address +1, which it makes actually sense. So the byte 1F is located at 42E77 as a virtual address. What we're going to do now is to find out what is its original offset, or in other words, its real position inside the file itself. In order to achieve this, we need some extra information about this executable file that we can obtain from the header of the Windows executable file format, or otherwise called the PE file format, which stands for Portable Executable File Format. So we can press on Memory Map Window button, which is this one here, and we can observe the sections of the image of the executable in memory. So we know that the address of this byte, or actually of this instruction, is 42E76, which is, as we said, the address of the first byte of the instruction. So this instruction is located in the first section. If you do the math, you can understand that if you add this value here, which is the size in memory of the first section, it corresponds to an address bigger than that, which means that we are inside that range. And if you completely scroll up, you see that in this section the first address is 41,000. So, and you can verify this from here. But this information is not enough. We also need to know more information about this specific section as defined inside the header. So we select the starting address of the executable in memory, we right click and we select dump in CPU. Then we go here and we select special PE header in order to decode these structures as readable in a readable format. So we can see here that in offset 3C there is the offset like a pointer to the PE header. So at offset 200 we should find the PE header, the start of it. So if we scroll down, we see here the start of the PE header. We are interested in the information related to the sections of this executable. So we scroll down and here is the structure that contains all the information about the first section of the executable. We can see the virtual size again. We can also see the virtual address, which is actually the relative address from the beginning of the executable in memory. So you can see here that the starting address is 400,000 hex and the first section starts at 401,000. Then you can, as you see, the virtual address is 1000, so it's the beginning plus 1000 hex. This is the size of the raw data, which means the actual size of this section inside the file itself. This is very important. This is what we are going to need later. This is the pointer to raw data, which means this is the offset where this section starts in the file on disk. We see that in memory this is 1000 hex, but on the file, on the physical file, is 600. So now we have all the necessary information. We know what is the beginning of this section in memory, which is 401,000 hex. We know the beginning of this executable in memory, and we also know what is the real start of this section in the physical file. And of course, we also know what is the beginning, the address, the virtual address of this instruction here. So what we really need to do is to do some simple math, and of course combined with logic. So what we have is the image base. We also have the virtual address of the first section. We have the offset, which is we have the offset of the first section in the physical file, and we have the virtual address of the instruction. which is corresponds, as we said, on the first byte of the instruction. So what we need to do now is to find the difference between the start of the file and this address here. So let's find out what would be the offset of that byte if the executable sections had the same alignment in the file and in memory. But as we know, in memory the alignment, for example, of the first section in relation to the beginning of the executable is 1000, but in file it's 600. But let's see what this would be. So let's just subtract from this address here the address of the first section. So we would know what would be its offset in memory, the offset of the first byte of this instruction here. So the result is 1E76, and as we know, the alignment is different. So this is actually what would be the position from the beginning of the file if we didn't have a gap between the header and the first section, which in the file the difference is 600. So the first section starts after 600 bytes. But remember that these values are hexadecimal. So what we can do is, since we know that there is this gap, we have to add this value to this value here. So we do the math, is 2476. So let's verify this by loading the executable into the hex editor. You can see the start of the executable file. Then if you scroll down, you see that the first section starts in the offset 600. And let's go to this offset here. So here it is. These are the bytes of the instruction we're looking for. You can verify this. So let's just know both bytes. So in this case it says that the file is used by another process because we are already debugging it. So what we can do is just shut down the process and modify, and then save as. Batch 2. So let's test with a random code, and we see that it accepts our code even if it is invalid. So what you can do right now is play more with this challenge. Try to do both modifications in memory using old debugger and also using the hex editor. Also play around with these values here. Make sure that you fully understand the concepts we just discussed, because most probably there is going to be a question about this subject during the final examination, and generally dedicate as more time as you can on whatever we do, because it's very important that you really understand what we discuss about and you don't just try and copy paste and just follow this video. You really need to understand that the video is made in order to help you understand better the written parts, and not just to skip the written part, go through the video, just do a quick let's say overview of the full chapter. So I hope you really had fun with what we just did in the first video. So see you in the next one.